Okay, this we're going to talk about radiation, or how the Earth gets its energy. So I wanted to look at an aspect of that. Uh, Energy comes to the Earth from the sun, and each piece of energy has some kind of wavelength associated with it. We're going to talk about what wavelengths are later. But let's just say that for most of the sun's energy, it's called ultraviolet radiation. And for the Earth, it's called infrared radiation. And the Earth being the atmosphere, any part of the atmosphere, the ground, whatever. So I wanted to explore this infrared radiation and how meteorologists use it to help understand the atmosphere. So let's look at, I have a choice of goes east or goes west. Why don't we try goes east today and just see what we have options of. So goes east is a approximately. And I wanted to give you an example of how meteorologists look at the weather. Well, what I'd be interested in was I'd like to know how clouds are moving. Maybe I'd like to know where lightning is. Maybe I'd like to know where moisture content changes or what the winds are. So all of that is done by looking at the infrared radiation from the Earth. We have different ways of looking at that. For example, I could look at a visual image of the United States and part of the Atlantic. This will show you what is going on now, as if you were sitting in space looking out. Let's take a look at that space sitting out over here. Over the United States, there's a significant snow cover, and you can actually see it on the visible image here. So the snow is right here, starting on the Appalachian Mountains, going across there, out across Tennessee, Kentucky, and all that. The other areas you're mostly looking at are clouds. Notice the clouds off the eastern coast of the United States. Think about this. You have cold, very cold air moving over warm ocean, and there is warm ocean relative to this air that causes clouds. However, you also have into the Midwest. These are clouds being pulled up out of the Gulf of Mexico as moisture is coming up. So all of this, I'm observing this image. And so that's a lot of information that you're able to get from a gauge. So let's go back one and see if we can look, for example, at some other parts of the ones I wanted to take a quick peek at. Well, this is now moving. You can see the loop of the satellite. And I wanted to just show you some options here that are available for goes east. We have lightning. I don't think and we also you can look through these later. Green and blue images here, which basically just show you some options of looking at curves. All color curves on satellite are red, green, or blue, and how they interact to each other. How we may have a larger red or a larger green or a larger blue makes a color curve. So by knowing that, we can explore things. One of the interesting things is that water vapor emits at a certain range. So we curves of water vapor. Maybe we can look at temperatures using infrared. Maybe we can combine these. There's actually 16 different channels here that we can explore on a satellite image. So kind of neat to know all that is available to us as a meteorologist, and we can understand basically just using the infrared radiation from the Earth to make a lot better understanding of what is happening. When I came into Weather Service, over 45 years ago now, we got one image, always either visible or infrared, covering the entire United States every hour. Now I can get these updated. They're updated 5 minutes on this web page, but they're literally are minute by minute changes that actually I can go find on another web page. Think about that difference. I was seeing a satellite picture once an hour with only 2 colors. Now I can see all these different channels, understand how water vapor is changing, understand how air masses are changing, understand where lightning is. All of that was not available. So we have made major strides in all of this over the last years. I wanted to look at this week's notes that were here. If we were to look at a slideshow, and we're going to just talk about solar and terrestrial radiation. And that means we want to look at how these change with time. Basically, the Earth has a bunch of radiation coming into it from the sun, and it emits about the same amount of energy. So as we have a stable environment, we're really not in the sense of energy flow changing significantly. So we have electromagnetic radiation. You ever think about a microwave? If you ever put your hands in a microwave and it was on, you'd burn yourself badly, very quickly. That is a form of radiation. The sun emits radiation. You can see it. It's very bright, very powerful. The Earth emits radiation. You emit radiation. I can see you as a person when I look at you. That is because you're emitting radiation. All of this is under different wavelengths, what we can look at here. What is a wavelength? Well, I tend to think of it in terms of water. There's ocean waves, just like we talk about electromagnetic waves. There are ocean waves. And if I have a wave that hits me, then goes down to the bottom and then comes back up and the next one hits me, the distance between those two waves tops is a wavelength. So the same holds for electromagnetic radiation. And since electromagnetic radiation always moves at the same speed, the speed of light, the more the wavelengths are closer together, the more powerful that radiation is. The further apart they are, the less powerful it is. We think of almost all things as black bodies. It's not really true, but we tend to approximate that. So that means that all the radiation that your body absorbs is being re-emitted back out into space, hopefully. Most of it anyways. The same with the planet. By doing that, we get an estimate of how intense the radiation is coming from you based on your temperature. So both the sun and the Earth are kind of black bodies. So most of that intense radiation is at a much shorter wavelength from the sun than it is from the Earth. And that is what's called as Wend's displacement. Why is that important? Well, think about it. The sun is many, many, many times higher than the Earth's temperature. So the bottom of the equation is temperature. So if the sun is much, much, much hotter than the Earth, the wavelength is going to be much shorter. Another one is the power. How powerful is that wavelength? Or how powerful is the radiation coming from the sun? Well, we've estimated that it's approximately the 4th times to the 4th power of the temperature. Well, you think about it. Earth's temperature. If you did it in Celsius, maybe 25 degrees, 20 degrees Celsius. Sun's temperature, millions of 900,000 degrees Celsius. Now, do that to the fourth power, and you see there is a tremendous amount more radiation coming from the sun than there is from the earth. Now, as you go out from the sun, you reduce the amount of radiation hitting the planet. So, Venus is closer to the sun, has more radiation hitting it. We'll say that approximately an inverse every distance, double the distance from the sun, we lose a significant part of the amount of our radiation. So say we were 4 times further out than the Earth. Well, R would be 4 there, so that would be the 1/16th of the amount of radiation hitting it. So you can see as you go out, it reduces very quickly. All right, now's where I'm going to confuse you, and I'm trying not to. I really wish we could have looked at this with a nice, bright flashlight. But you see a picture of a flashlight on your right here. Think about it as that flashlight represents the sun. So if I am at the equator, and we'll say this is an equinox like March 21st or September 21st, the sun would be directly over my head. Notice, it's not covering a very big area, but it's pretty intense over that area. Now, I live up here. I am, 30 to 40 degrees north, approximately, somewhere in that range, most of the United States is. So that means that that sun that was directly over the equator actually had an angle of 40 degrees. So if you were to look at that angle here, you would make a 40-degree angle there. If you had a protractor, that would be how the sun looks to the northern part of the United States. Notice how it spreads out over a much larger area. Same amount of light coming in, same amount of energy coming in, but now it's covering a larger area. So any spot on that area is not getting as much sun, not getting as much energy. So the further north or south away from the direct line of sight of the sun, you're getting less and less energy. Now, what that means is the Earth does not receive all the sun's energy the same. It's spread out. And there's always going to be, in the wintertime up north here, very little energy reaches the North Pole. Matter of fact, none from the sun. By the same token, some sun is now down on the South Pole. It's getting some energy. So you can see how it fluctuates. With that in mind, that has a huge, huge impact on our temperatures. For example, if you look at Antarctica here in the dark blue, notice from basically late March to September, there is no energy coming into Antarctica at all. Now, look at the equator. Singapore, very close to the equator, and not much change in temperature throughout the year. However, as the sun comes back north, we get a significant rise in temperature up in our latitude, and then in the wintertime, we get a significant drop. So the sun's radiation plays a big role in our temperatures. And you can see here, the Earth's tilt is the same. It never changes. It's 23.5 degrees. However, depending on where it is in its orbit around the sun, huge difference on how that sun is hitting the Earth. So, interestingly, between scattering, reflection, absorption, all the Earth's energy transmitted to the Earth's surface must be accounted for from the sun. So, there are 3 different things here we're talking about: scattering, reflection, and absorption. So what the heck are we talking about? Well, scattering. Take you have a cloud, or maybe a dust object in the sky, about a dust. The sun hits that. It's scattered in all different directions, not just any one. So some of the energy from that sun then is going back out in space. Some of it's coming to the ground. Some of it's coming at different angles into the ground. That is scattering. Reflection. Think about the bright snow I just showed you on a satellite image there. That is albedo or reflection. The higher the albedo is, the more sunlight is reflected. Snow is very, very high albedo. So if you're up on the North Pole, a lot of the sunlight is sent back out into the space. Absorption is what we absorb. The ozone layer absorbs a lot of the UV atmosphere coming in. And that protects us from that UV radiation reaching us and keeps us from getting sick, basically cancer. You can see here the higher the albedo, changes in sunlight. And here is basically how all these things work. Basically, reflected from the Earth's atmosphere system is 30%. Absorbed by the Earth itself, 47%, and absorbed by the atmosphere itself, 23%, making up the total. The principal recipient of solar radiation is the Earth's surface. So it gets hotter at the Earth's surface than the rest of the atmosphere in the vertical, typically. All right, there's another component here. If we took only the sun's radiation, we couldn't live on the Earth. Why? Because we would not be as warm as we are. There's something called the greenhouse effect. All right, I said that the sun comes in ultraviolet radiation, very short wavelength. The Earth emits an infrared radiation, a longer wavelength. There are gases such as carbon dioxide, methane, and others. Water vapor, outstanding at absorbing infrared radiation, but will allow that shortwave radiation to come on in. So what happens is they absorb it. That greenhouse gas absorbs it and sends some of that radiation back to Earth because it's a black body. It's going to emit that radiation, and some of it goes into space. So we wind up with more information, more radiation coming back, more heating. It allows the Earth to be hotter than it would normally without greenhouse gases. So yes, greenhouse gases can be a good thing. Can be. However, if you get too much of a greenhouse gas, you get a bad thing. So let's see how that might play out. If you were on the Gulf Coast, say, living there, or looking at the desert Southwest, both are about the same latitude, receiving the same amount of sunlight. If you're in the Gulf Coast, you got the Gulf of Mexico, the Atlantic Ocean there. You're humid. You have a lot of water vapor typically in your air. Water vapor very well absorbs infrared radiation. So in the daytime, sun's radiation comes in. Nighttime, that infrared radiation from the Earth, way stronger than the sun's radiation, which is gone now. So it's wanting to go back out into space. When it's going back out, it hits this water vapor, it's absorbed, and some of that energy is left back to come back to Earth. It keeps the nighttime temperatures warmer. Now, if I'm in the desert, I have very little water vapor, the nighttime temperature is going to get much colder. So you can see the impact water vapor has. Another one here we talked about is the calendar effect, which is basically just looking at the carbon dioxide and how it's increased. During the year, during the seasons, particularly in the northern hemisphere, which has larger continents, we actually reduce the amount of carbon dioxide because of photosynthesis during the summer. However, during the winters, we don't have that. And you can see the curve of carbon dioxide has been increasing faster and faster. So that's what's interesting about global warming. So hope you got a little bit out of this, and please let me know if you have any questions.